It does require Windows 7. We've have some testing on 8 and 10 that shows it works, but it's not verified. We haven't had as much hours on Windows 8 and 10 as we have on Windows 7. So it does work, but it's not 100% verified yet. It requires .NET Framework 4.0, and this will be the installer for KMS will detect whether or not that's there. So it'll prompt the customer to actually download this if it's not present. And then it does require, we're using KSDK 1.3. We do not, right now, all of the motor control solutions within NXP are not moving to KSDK 2.0 yet. They're going to stay on 1.3 even after the 2.0 release. And that'll be done in a coordinated movement at some later date. It also requires one IDE. So it requires either IAR, version 7.4 or newer, and Kinetis Design Studio 3.03. So it requires one of those two. That's so it can do the automated compile and download and everything. So one thing to point out is that some of the slides, so we've given you a bunch of slides, and I'm going to present a subset of all of those slides. But there's a bunch more in there that are for your reference, so you can look back to. But there are some that are marked confidential, subject to NDA. These are confidential between Linestream and Freescale, or NXP. Sorry. So do not share them with customers without prior approval. Don't email them to customers.
Sure.
Just want to make sure so all the slides that are marked confidential, subject to NDA, are subject to that. Everything that's not marked with this can be shared with customers. So this describes the PC tool architecture of KMS. So this is the side that runs on the PC. And this is the side that runs on the target. So it has our reference design. And it talks to a small agent inside the reference design. That's what handles the communication between PC and MCU. And right now that operates over the serial link. This agent is actually open code. So if the customer wanted to change it to operate over CAN, as long as they could have a CAN to serial connected to their PC, it would still work.
But they have to handle the host side for Cisco, right?
Not the host side, because as long as they had an adapter that presented that they could hook CAN up to,
okay,
and then presented as a COM port to the PC,
yep.
it would still work.
Okay, yeah, okay, correct.
So what this does, this fills this what's called the data model. So this data model is where we store all the things that are going on inside the MCU, and we scale them into human readable values. And they get rendered as an element in the GUI. So that gets shown up to the customer as a plot, a text, an input box, or an output box, or a knob, or a checkbox. There's a bunch of different GUI elements, and they're just kind of ways of visualizing things that exist in the data model, which are things that exist on the MCU. Then we have this configuration space. So this is a collection of all the elements. So if we have a position control GUI, that's going to be different from a sensorless velocity GUI, is going to be different from a sensored velocity GUI. And that could even be different it'll be slightly different depending on freedom versus tower versus high voltage. So depending on that matrix, we have a different configuration file for each part of the matrix. So this way we're presenting the most important information to the customer. We're not presenting them things they don't care about. We're presenting them only the things they care about. And then deployment is the actual PC software side, so the exe file. So that way you can kind of see how it's kind of all structured, basically. And then KMS installs into 2 locations on the hard drive. It installs into program files. So this can be relocated by the installer. So you can, when you guys all ran the installer, you could have chosen to install KMS in a different location than the default. And what is in here is just what we call the kernel files. This is the core of KMS, so it knows how to actually do all the things it needs to do. It also contains the reference projects, which we've made individually versioned, so we can update them as we go. So let's say, imagine a quarter after launch, we want to make an update to the reference projects. we can update just the reference projects and not have to update all of KMS, which makes it really easy to keep giving new updates to customers. And we also have what we call the personal files. So these install under C users, user documents, so the My Documents folder, and then KMS _ version number. So right now we're on KMS 1.17.0. So this is the version. So once we go to 1.18.0, we'll have a new one. It'll be KMS _ 1.18.0. So these are non-relocatable. It will only install to this location. That's enforced because we need to know where this is. This is where KMS will writes a lot of data out to. This is where it default unzips all the reference projects. This is where it stores things, where it stores traces. It's an important location for us, and so we don't move it. So it really holds all the configuration files, documentation, example motion sequences, the trace logs. So when a crash happens, that's kind of your debugging is the trace log, and it's the default location for saved projects. So if we actually, so we actually go look at that folder. So I go to My Documents, KMS 1.17.0. So right, you can see these are all the things that it's saving here. It's all kind of my intermediate and workspace kind of values and data. So my saved projects, this is every project I've opened with KMS. Every time I do a new, it defaults to just make a new folder here. And similarly, I can look at this archive, and this shows me all of the previous 7 days worth of KMS activity. So if I had a problem with the GUI where it crashed, I can go to this archive and pull the file out that represents that run of KMS and figure out what happened.
Okay.
So it's just a good debug way for us to look at what happened and try and figure it out. Then like support time capsule, saved. If I want to save a plot, it defaults to here. So it's kind of an important place for us. And then KMS is really the PC side has 3 components. It has motor tuner, motor manager, and motion sequence builder. So we kind of talked through these already, right? Motor tuner is your first 5 minutes with the customer of take their motor and get it spinning. So it's it's a wizardy approach to just identify the motor and get it spinning. Everything that you can do in tuner, you can do in manager. Tuner is a subset of manager. It's just presented in this kind of step-based wizard approach. And so its goal is to set up the whole system and just kind of let the customer start their design. So manager is where we pull out and lets you exposes a lot more of motor control parameters and settings and lets them actually get and dive in and figure out what's going on. So it's designed to allow them to adjust critical values for their motor and end application. And then motion sequence builder, it builds out that application sequence. So that's how we build up our ceiling fan. It's this kind of motion sequence builder. So it generates MCU code for us. So inside of KMS, we have these scripts, and these are what kind of automate a lot of the work for the customer. So there's 4 key scripts within KMS. The first one is the parameter identification. So when you click the identify parameters button, it goes out and runs this script. So the important thing to note about this script is that when you click that button, it will go overwrite all of the settings you have, because it assumes that you've disconnected your old motor and plugged in a brand new motor. So it does not assume you want to retain any setting. It will erase all of them and set them back to the defaults.
Yeah.
So it's something to be aware of with a customer. If you've gone in and changed a couple things and decided you want to go back to parameter identification, you're going to lose your changes. You need to make them again. And that was done by design because we assume that you've connected a brand new motor.
But
Yeah.
customer can save it, right? So they save the parameter.
Of course, yeah, they could save the KMS file and they can save that system.h off. But I just want to know that if you're just kind of working through the GUI, if you click that button again, it'll go overwrite everything you've done.
Okay.
But it won't. But you still can save, before you do that, to retain stuff.
Okay.
It also will do some adaptation. It'll adapt the identification based on faults. So if we have overcurrent faults, it'll kind of adjust the current thresholds, for example. It'll adjust some speed thresholds. It'll do some automatic adjustment during the identification process. It'll also adapt the drive based on the results. So the example for this is that if the motor is a low inductance motor, it'll increase the PWM frequency, because in order to drive a low inductance motor, we need to switch faster. So it'll do these kind of adjustments to make it easier for customers to have a good experience. It'll calculate all the drive defaults for them. It'll kind of tune all the motor control. So the next one is inertia identification. So this one just runs the inertia identification routine. And it'll adapt the routine based on what faults it sees. So if it sees for example, a motor overspeed fault, that tends to mean that it needs to go and adjust the ramp time setting, which is one of the settings for it. So it'll automatically do that. It's designed to be iterative. So if you click the button and it fails, it'll prompt you and say, it failed, but it's updated the configuration values, please try again. So that's the thing to watch for when you're doing the inertia identification, is that it'll tell you if it was able to adapt or if it wasn't able to adapt. And so it might take multiple tries to get it to actually complete. So the reason we don't automatically just keep running is because what if you're working with a customer who's like an elevator door customer, and they have their big doors set up. So you want it to be in the position where it can run the doors to identify the inertia. But you can only do that when the doors are open, right? If they're closed, they're just going to run into each other.
Yeah.
So you want to so you might have to move the mechanical system in order to run the inertia identification multiple times. So that's the reason why we made it so it doesn't automatically just keep trying until it succeeds. We wanted the customer to be able to move the operation and know that the whole machine was going to spin. And the last two are fairly similar. It's update motor drive configuration. So this takes all of the GUI settings and pushes them into the MCU and does what we call a soft reset. So it actually resets the motor drive. So we'll go and reconfigure the entire complete motor drive all at once. So this way it'll push all the settings in one shot. You won't have a case where you have half bad settings and half good settings. We want to make sure that all the settings are good at the same time. So that's what that script does. And store motor information is similar in that it will push all the data in to the MCU. So it'll actually run this update motor drive configuration script. It'll just run it, but then it'll take that motor drive configuration and save it to a header file. So it updates the reference project with that new header file. So this way, when you recompile and bring the processor up, it'll come up with the motor that you want to use. Okay, so I'm sorry, I feel like I'm going really fast, but
That's fine.
I'm trying to give you guys all the information really.
Yeah.
So if you have questions, please ask.
Yeah.
So this is what our block diagram looks like. I'm gonna grab my pointer real quick. So it's a standard field-oriented control reference design. So it has here's our trajectory generation. So this is what tells the speed controller what speed to run, which provides the reference to the current regulator, which has built-in DC bus compensation, which feeds the voltages to the park, which tells the space vector block what duty cycles to write to the flex timer, which actually goes and runs the motor switches out to the motor. And then we sense the feedback current through our shunt resistors, and we also sense the DC bus. That goes through the ADC on the MCU, goes in the feedback block to the Clark, to the park and estimator, and back to the current. So it's a very typical FOC layout. So it's something that if you look at almost any reference design or paper about field-oriented control, it's going to be this exact layout. So it's very typical. Now what we have done is the way that the code is laid out in terms of open source versus closed source. All of the connection points between all of these blocks is open source. So the customers can see all the interactions, but the insides of all these blocks are closed source. So for example, we have some special IP for the speed controller. It's a better speed controller than a typical speed controller. So since it's our custom IP, we don't want to expose that to the customer. So it's provided as all these blocks are provided as a library.
So only the speed, the block speed is library.
No,
Speed and current.
yeah, speed, current, estimator, park, every one of these blocks, except feedback block is not. But that's because we wanted to make that very flexible.
Okay.
So it might help if on this next slide. I think this lays it out pretty good. So up here at the top level is what we call the user application code. So this is everything that's generated, everything the customer generates. So this is their value add.
Yeah.
So the example file for that would be the main.c. Right? That needs to be open source because that's really where the customer is going to start to put their code into the project. But then down a level is what we call the KMS glue logic. So that's how all the motor control blocks are connected together.
Could you back to the previous? Yeah.
Yeah.
So the best
The black lines.
Yeah, the DRV.C is which one is it?
So the DRV.C is the collection, makes calls to all of these.
Okay.
So the DRV.C is this whole diagram.
Okay.
So what you see in the DRV.C, and I'll show it and we can talk through it a little bit more too, is you'll see the connection points between all these. So all these black lines are called out in the DRV.C.
Okay.
So it's the connection amongst all the motor control blocks. But the actual motor control algorithms are in a library. So this library file, for example. And that's in both the secure region that Philip talked about in the other conference room, that has that secure region that we do not want the customer to erase, and this library. And that's closed source.
Okay, I see the orange, the color in orange is the most of them are in library.
Yeah, the color I was trying to show who provided. So right, customer in green, line stream is kind of this orange, and Freescale is or NXP in blue.
Yeah.
And so the motor control algorithms themselves are closed source. But then the system interface, so how this motor control actually talks to the SDK, that's open source. So that's what in our ADC sys layer, or that's an example, is the system layer. So the ADC, the PWM, the QEI, and QEI for encoder, and UART are all open source. How we actually interface to those, and we do use the SDK for that. So this way, it's easy for customers to switch between different MCUs. So if they start the reference design, they start the tower board using the 512, want to switch to the 128K version, it's very, very easy with the SDK. And obviously the hardware registers are open source, they're described in the reference manual. This is kind of how the code is laid out from if you look at you want to look at it as like a different set of layers in terms of where the knowledge is and what's open and closed. So let's actually take a look at the software. I think that'll help. So if we look at the main.c, this is where we kind of do all the initializations. So there's just a lot of little global variables up here that handle communication. But we also call out our ISRs. So KMS uses what's called a dual ISR approach. So we use the ADC ISR to trigger when to actually call the motor control, so when to actually run the FOC. Then we use a software ISR to trigger the slow interrupt. So all the speed loop, the trajectory, things that need to happen on a regular tick, but not every single PWM tick are in the slow loop. So this was by design, so this way that we can have that slow interrupt be interrupted at a higher frequency by the ADC, because that's the most important ISR. So we have that as a higher priority. So if we go into the ADC ISR, we basically, you can see everything we're doing here. It's nothing super fancy. So we read the raw ADC values. We There's also acknowledges the interrupt. Then we have our update at fast tick function. Oops, wrong one. Which actually will do our feedback run, which takes our raw ADC, calculates it, and converts it into values that are usable by the motor control algorithm. So it'll read the raw ADC and then convert the value into a current reading or a voltage reading. Then it calls DRV update at fast tick, which this is our main motor control function. So it reads, so it'll decide whether or not the PWMs are enabled. Then it'll just start running that motor control algorithm in the block diagram. So you see Clark _ run. So we've tried to name everything, and we haven't tried, we have named everything so that this Clark is a module. So it's the Clark transform, yeah.
So is it a clock? It's also a library.
It's also in library.
Oh.
And that was just to
It's
obviously
not open.
Not open. And there's no IP in a Clark transform, but we kept it closed for simplicity, just to make it a little simpler interface.
Okay.
Yeah. And so, for example, like Clark is the name here, and you'll see the same name in this. See Clark. So we've tried to, all the names are aligned, so it's very obvious what is what. Tried to make it, our goal was trying to make it simple and make it easy.
Yeah.
And so you can see the Clark takes the feedback.output, so it takes in the currents, and then it'll pass those to the estimator. So estimator update fast tick. One of its inputs is Clark output vector. So let's see how that's that black connection point on the diagram from the Clark block to the estimator block. And so so basically this is kind of how it shows you how the drive's connected. So if let's say a customer has their own version of a Clark block that they want to implement, as long as it has the same interface, so as long as it has this interface, they can still use it. So as long as they can update everything that downstream of the Clark transform, they can use their own. So it's the same with the space vector, it'd be the same with the current regulator, it'd be the same with the field weakening or the startup. As long as they match they'll align to our interface, should just plug in very seamlessly. Okay, does that kind of make sense so far? Any questions so far? Okay.
You talked about the user block?
Yeah, I will.
Okay.
Okay. So I think it's helpful to kind of talk about how we architected this software a little bit. So that's we talked about what the block diagram looks like. We talked about kind of the different access points or the layers that customers can touch. But all of our motor control blocks are written in what we call block and pin. So everything is self-contained and unit testable. And then it has very specific output ports. So each block is self-contained software. It has input, output, and configuration pins. So it's kind of like, it allows our goal is to make it so it's more like Legos with software, is you just kind of connect it all together. So you just kind of, or maybe wiring might be a better example. You just kind of wire it up and everything will just work. So each block is defined as a software module. So if we go back to this, so each block here is a software module. So there'll be a header file for every single one of these in the reference project. So like we showed, the example we were showing was the clark.h file. And it's just called clark.h. Makes it very easy for them to see everything's aligned. So there isn't any need for additional external components to run each module. Everything is self-contained, and it can be tested individually. And then again, the connection points is open code. That's in the drv.c. And then so each module has the following each module has kind of the following components. So all of them have a configuration structure, an output structure, and a private structure. So the configuration is anything that can be updated at runtime. That's like its setting. So for example, in the speed controller bandwidth is a configuration because we can update it continuously. But the speed controller sample time is not in the configuration structure. And that's because we only want to update it once. Or we want to update it and when we reconfigure the whole block, not continuously. And the output structure contains the output values of the block. So what things get updated when you actually call the main run function of a block. And the private is just internal only memory. So things we don't necessarily want people to touch. We declare it as bulk memory, so that way it's not, you don't know the contents of that memory. It's just seen as just empty, it's just memory with random data in it to the end user. And then for functions, they only work on the address of the module. So you always have to pass a pointer to a module in order to actually run it. It doesn't assume there's a statically declared Clark transform. That's the only Clark transform it can work on. You could have 3 or 4 or 5 instances of Clark transform, and you can keep calling the same function, passing it new pointers every time. That was done by design so we can scale to support multi-motor solutions with KMS. So in terms of everything, every function has initialization, which its entire job is to just zero out the memory. So it makes sure that the amount of memory, the size of the object is the right size, and it zeroes it out. And then there's a configuration. So this actually takes input values and then calculates any needed values for the private memory. And so it does require inputs to calculate its internal configuration. So anything that's an input to the configuration function can only be changed when you rerun the configuration function. And then run and update does the work of the module. So it requires the inputs that are the inputs to the block. Okay. And the other thing I wanted to mention is everything is documented using Doxygen. So we have an API reference guide that describes everything. And it's actually it's generated from the reference project. So everything in the API reference guide is also in the code comments of the reference project. So again, our goal is alignment, trying to make it as simple as possible. So let me pause right here and let's jump to the code and look at some header files and so we can kind of see what I meant when I talked about all this. So I think a really easy one to look at is the current controller. Let me find it. So it's called current.h is the current controller. And so here's its output. Current_output is stator reference voltage DQ. Okay? So its output is the reference voltage that's going to pass to the iPark transform, which is going to pass to the space vector block. Okay? And here's its configuration. It's these PID, PI parameters. So these are just configuration structures for a PI controller. Then here's the complete current module. It has its configuration, its output, and then its private data. And so the initialization is current_init. So you pass it a pointer to your current. You pass it the size of that block. And this is just so we can zero out the memory and make sure that we've allocated enough memory for it. And then the configuration. So the configuration takes a pointer to the current module it should work on. It also takes a pointer to a configuration, a structure of current_config. So it's kind of, the reason it does this is so that way the system.h, remember this is our generated header file. The system.h is our generated header file. The reason it takes this current_config in the config function is so that the system.h let me open this as well, can store all the defaults. So you see here's current underscore config underscore T. So these are the current controller defaults that it's going to use at power up. So we can store them in this header file and then pass them into the current block. So that way when we do a reset, we're going to go update all of the configurations all at once. And so current also takes a couple other things as inputs. It takes the FOC sample time, and then the filter frequency, as well as the voltage gain. And so it's going to take all those in and then set up its internal memory, its private memory, and then it's able to start executing. And then it has the ability to reset the controller, so to reset its integrators. It can reset its filters separately, and here's the current run. So when you're running any kind of PI, any kind of control system, you always need a reference and a feedback. So that's what basically what this thing takes. Is it takes the DC bus, the inverse DC bus, the current reference, and the current feedback. So these are considered the input pins for the current module. This is what we want in order to actually execute. So if I jump back to the drive, let's show you where all these are called in the drive, in the drv.c. I think that'll help too. So if I search for current underscore init, okay, it's in this function called drv init, drive init. So when it wants to initialize the entire drive, it's going to go call the init and config for every block that exists.
So user just only need to code drv init, and you will automatically to initial all the parameters.
Exactly. And then we have the ability, so we've actually added the ability in the code to recall this. So when you click update motor drive configurations, it updates this system parameters header file, or system parameters underscore T, which exists here. So it updates all of the configs. That's all this is just a list of all the configurations. And this is in system.h. So it updates a copy of this structure and then reinitializes the whole drive every time you click update motor parameters in the GUI.
Yeah.
So that way we can update the whole drive all at once. And so we always want to do an init and config. So we'll zero the memory and then configure the memory. It's this pattern of zero memory, configure memory, and so on. So here's our current, right? We're passing in the address we want to work on, configuration, say FOC sample time, and a pound. So here's a pound defined for our filter frequency. And this is as accessible if customers want to change it. We kind of just picked generally good defaults, but if they feel strongly about changing it, that's fine. And then a voltage gain, and then a gain value. And then if we look for current underscore run, it's down here. And this is in the, I'm going to scroll up a little bit, DRV update at fast tick, because we want to update the current controller every time you run the FOC. So it calls it right here. And so we pass it the address we want to work with. Oh, I have to fix that. We pass it the VDC, the inverse VDC, as well as this temp stator reference current and the output of the park transform, which is our feedback current. So this temp stator reference current can come from two different sources. It can come from the user output DRV command, or it can come from startup, or it can come from three sources, or the speed controller. So depending on what mode the drive's operating in, it'll pick the references differently, depending on the operating mode. So this is all kind of here. And so if customers, let's say a customer is going to only run in torque control mode, then they wouldn't necessarily need this code up here because they don't have a speed controller. So they can remove it.
there is also okay because the code will not jump there.
Right. So they can keep it there, or they can remove it if they need to save memory.
Yeah.
It's kind of up to the customer.
Okay.
Okay, so that's how we do it on time. Okay, still good.
10 more minutes.
Oh, that's it?
Yeah.
Okay. So the other thing I want to talk about is the customer code interaction. So inside of the KMS firmware, there's 3 kind of super blocks.
Super blocks.
Yeah. There's the FOC or the DRV, the drive, the actual motor control algorithm. And then there's what's called the DSM, drive state machine.
Okay.
So this is what controls the drive. This is what says run as a speed controller, run as a current controller, run as a voltage controller.
Okay.
It also monitors the drive for faults. So when we were seeing those peak over current faults, the DSM was triggering that and saying, there's a problem, we need to stop.
Yeah.
So it issued the problem up to the customer, up to the user, but also stopped the drive. So all the fault handling is built into this DSM. And the user block is the customer input block. So what this is basically, it's just a big mux. So it'll take the input. So when we were setting a target speed in the GUI, it was writing to user command target speed. And then when you click the button to start speed control, that was setting user state to run speed. So this is the input, all the customer's input feeds into this block. So and it also contains the inertia block, the brake block, the SCM block, and the plan block. SCM stands for self-commissioning, so that's the parameter measurement block. So when customer says run self-commissioning, the user block will go to the self-commissioning and start executing it. Right, so this is kind of how this all works. It'll help. I think it's good to show the user.h. So these are all the modes that the user block can go into. And these are all what you would command to get the drive to do something. So you would set for run speed, right? You would set the user.state parameter to user run speed, and then it would start running in speed control mode. And if you wanted to stop it, you would set it back to user idle, which just means don't run, don't turn drive off, don't do anything. And so it also has a list of user commands. So these are all the commands that the customer can write to the user block. But it'll only pick the commands depending on the mode you select. So for example, if you set user run current, it's going to ignore these commands. It won't use them at all.
Sorry about this. You mean that if the user just code the current control mode, and you will not use the both.
It won't even use. It will only. So if you set user run current as the mode, as the state, it will only use these 2.
Oh, okay.
It won't use these. It won't use
Because
these.
it's a different module.
Exactly, because it's a different mode. Again, the user is just a mux.
Yeah.
That's all it is, just a big mux.
Yeah. Okay.
And it's the user and the DSM and the drive are all open source. So if the customer wants to go and let's say they want to remove self-commissioning from their project because they don't plan on doing it in the end application, they can go and pull it out of all these blocks and it'll save them memory. It won't compile in. So when we say the reference design is 40K, that's the complete reference design. That contains everything. So if customer doesn't want self-commissioning, inertia ID, right? If they don't want, they can remove it, save memory.
But before they do that, they may want to consider the need for it. If their application needs it,
Yeah.
it may need to be recalibrated some down the road or.
Honestly, in general, customer will in the beginning will survey the bigger memory first.
Right.
Yeah, and we will discuss with sales. We want this memory and with the lower price. So I think this case will not be happen.
I mean, it can get there. It can shrink pretty far if you're willing to cut out a lot of features. But since it's for the reference project, it has to be full featured. That's why it's kind of is what it is. Okay, then we've talked about that. Okay, the other thing I want to point out is that customers, we use the complete ADC resources for motor control, but customers can still add their own channels to be sampled. So we'll do the motor control sampling, and then we'll do a customer sampling with this ADC round robin enabled. So if you set this to true, every time through the ISR, after it does a motor control sample, it'll go sample these two channels. So this can be adjusted by the customer. So let's say I want to sample 4 different channels. I need to tell it how many channels I want to sample. So I'll say 4. Let's say I want to sample channel 6, 7, 8, 9. And I want to sample this channel every single time. So now what'll happen in this configuration is it'll sample 23 and 6 on ISR 1, ISR 2, 23 and 7, ISR 3, 23 and 8, ISR 4, 23 and 9, and then ISR 5, it'll be back to 23 and 6. So it'll do 2, 2, 2, 2. It'll just kind of keep rotating through every ISR. And it stores the results in these static registers, so they don't get overwritten. So if so let's say that this is my temperature sensor, for example. I'm only reading it in the background loop, so I read it every 2 seconds. The data will always be inside of ADC1 results index position 1, and it'll always be there. It won't get overwritten because it'll just keep updating new values there. So this way the data is preserved for the customer use, and they can set up to sample these ADCs at a slower decimated rate from the motor control ISR. So we'll do a software triggered sample, and then we'll reconfigure the ADC to be for motor control again. Because customers are going to want to use ADC's channels for other things other than just motor control. Everything make sense so far? Okay, how much time we have left? 10 minutes? Okay, so what questions do you guys have right now?
So far, follow.
The PC GUI side, can we cover any of that? Do we have time for that?
I guess what were you thinking? We talked a lot about it.
The only thing I think of is position. Well, we haven't touched on position yet.
So it's on the list of control types. We picked sensorless velocity for our work today. It supports position control as well. And so the big difference between position control and sensorless is that we also need to know the encoder lines for position control. We need to know how many lines are on the code wheel for position control. So for example, like you have an encoder on your motor right here. So you just need to know the number of lines on this encoder. And it also has to be...
How many lines in that motor?
That one is 2,000. You can tell by the part number, but it's going to be dependent on customer's motor.
The Linux motor does not have an encoder on it. It has a Hall effect sensor, and so it's not suitable for position control. You need to get a motor like that, or one of these motors, the Technic.
Okay, must have a encoder.
Must have encoder.
Okay.
And the software default out of box works with QEI, so ABZ, ABI encoders, but it can be adapted to work with absolute encoders. And it's going to be, but that's going to be up to the customer to do. But out of the box, we can work with QEI, or ABI, ABZ, no problem.
Some of the benefits I was trying to demonstrate yesterday was with the load sensitivity on position control. We have the ability to manage a load up to an 8x differential.
So it's actually inertia. So
And
if I've got this little inertia disc here where I can take these weights on and off, and the controller is good enough to handle taking these weights off and dropping the inertia by half, then putting the bigger weights on and making the inertia twice as big as the setting, and it's the same level of performance without retuning anything. So it allows customers who are doing robotic arms or any kind of a inertia changing application, but they don't have to retune the inertia or retune their controller for all the different inertia changes in their application. So it makes it very easy for customers to work with. So it still we had that one parameter tuned for the speed controller. In position, it's the exact same. It's just one gain for speed and position tuning. It tunes both at the same time. So I don't know if you've worked much with position systems, but they're notoriously very, very challenging to tune correctly. It's difficult to get them to actually work perfectly. With ours, it becomes very easy because all you just keep increasing the knob until it starts to oscillate, starts to vibrate, starts to have some overcurrents, and you back it down, and you're done tuning. Takes 5 minutes. While I used to work in robotics, and we spent months trying to tune our position controllers perfectly.
Mm-hmm.
So if I can take months to 5 minutes, it's huge savings for the customer. Makes their lives easier and gives them better results.
not everybody here is going to the customer. And Mark said he sent you a request to have you just stay
Okay.
and work with them. The people who are not going, they can continue the training. I don't need to have that motor back, so you can keep that motor for now. But I'm not sure what else. I think I got everything I need. I got the Technic position control cable though back from you.
我就是说，有些人可以留下来继续跟这个讨论。
Okay, I didn't see an email from him.
I didn't. He just said he just asked you. I don't know how he asked you.
I didn't get anything
Okay.
from him, so I don't know what he did.
You walked in, made that announcement, and walked out.
Okay, well, whatever. So he wants me to. He wants me to stay.
Yeah, if you
Okay.
can, that'd be great.
That's fine.
Are we going to be demonstrating sensorless velocity to the customer or position?
I think velocity is enough.
Okay, I won't need that then. If I
Yeah.
were to do position, I would gonna need that demo the weight. Okay.
你有他的名片吗？有。So, okay, now.
You okay?
Yeah. So what's the customer application?
I don't even know.
White good. I heard it's white good.
White good?